Okay, welcome to Quantum Tunneling and Spin, a 15-minute installment in this course, Physics X, Extraordinary Concepts in Physics. I'm your quantum coordinator, Robert Nemeroff, and this is Michigan Technological University. And so these lectures are all online. They require no textbook, and you can find them by searching for Starship Asterisk and Physics X on something like Google. So the idea is that we're just going to try to go to the really cool concepts of physics and not heavy on the math. So if you missed the delayed choice quantum eraser lab version up there in the previous lectures, you might want to go back and see that. Also the last one on was pretty interesting too, on the offshore experiment. So anyway, we're going to just touch on quantum tunneling. It's a purely quantum mechanical ability for a particle to go through a barrier. So I'm listing some strange quantum mechanical properties. So here you see a object here, and then here's a wall. And classically, it would just reflect off the wall. But here you see there's part of it, most of it does reflect off the wall in this case, but part of it tunnels through to the other side. So tunneling is a purely quantum mechanical phenomena. And here you see it shown in other ways. The size of the waveform, the amplitude of the waveform goes from high to low as it goes through. So typically the thicker the barrier, the less chance it will tunnel through. The less powerful on one side, barriers can be relatively opaque. Macroscopic objects have a diminishingly small chance of tunneling through a thick barrier. So quantum tunneling, though, although purely a quantum phenomena, is important for everyday life. For instance, radioactive decay. So you have radioactive decay happens all the time, helps us date things, for instance, carbon-14 dating. In radioactive decay, a particle will tunnel out of a nucleus. So this is a common phenomena which relies on quantum tunneling. There's also scanning tunneling microscopes where you put a needle down and there will be a tunneling electron current between the needle and a surface, and the amount of current can help you see very, very small things down to the atomic scale. One thing I didn't know before researching this lecture, and strangely enough I do research these lectures, enzymes apparently, a factor in their reaction rates apparently comes from tunneling. Don't ask me more right now, but I sure want to read more about that. Okay. So one thing I looked for, I thought someone might have done this calculation, but I was sadly ineffective in finding this calculation on the web. I found a lot of people who estimated it would be really small, or who said that we shouldn't even try to estimate it since it's so small. What are the chances of a human tunneling through a wall? So theoretically, if you were to run at that wall near you, and you know which one I'm talking about, you might be able to get through to the other side, just maybe. There's a much better chance you'll be struck by lightning 100 times in a clear day. Still, it could happen. It's very, very small, dimensionally small chance, and I really want someone to estimate just how small that is. So if you know the specific numerical estimation, please tell me. If you can find none, even if it's a ridiculously small number, 10 to the minus Google to the Google, send it through. I'm curious. It has educational interests properties. Okay. Now let's go to the Stern-Gerlach experiment, which is really interesting. Surprising. Somewhat not as surprising maybe as some of the delayed choice quantum eraser stuff, but here we have a beam of neutral particles with spin, enters a non-uniform magnetic field because the effect would go away if it was completely uniform. You need there to be a top and bottom defined by the magnetic field. Given that the particles can be divided into smaller particles that individually have electric charge, and that these particles are spinning, the non-uniform magnetic field would deflect a classical particle like this by an amount that depends on the orientation of the spin. So if you have your magnetic field like this, with more magnetic field lines at the top, say, and then you have a classical object which is spinning. You can tell classical objects by the little window that's drawn on there. Usually it shows their 3D spheres. Then the orientation of the So then you send this through an experiment. The orientation that you get out would be classically a continuum of deflections, or only classically it would be continuum of deflections. But you do this experiment now in reality. What do you get? Do you get a continuum of deflections, or do you get only two discrete deflections show up, corresponding to spin up and spin down for neutral particles? Which is it? Well, if it was just classical, we wouldn't be here now. So here is the Stern-Gerlach experiment. So here you have a furnace or some source. Here you have some kind of atoms, which can be even neutral hydrogen atoms, but it's easier with silver atoms. Here you have a big south magnet and a small north magnet. And these things go between the magnets, and then classically you would predict that there would be a continuum. Since the silver atoms can orient their spins in pretty much any direction, you would expect a continuum of deflections. And the ones that are all spin up would be maybe at the top, and all spin down would be at the bottom, and when it's in between, it would be one or the other. What do you see? The answer is only two discrete deflections show up, corresponding to spin up and spin down. So let's go back and show you. Well, if you looked closely, you could have seen this. But since nobody reads anything these days, I assumed you just glanced over that and didn't see the answer. Or if you did, good job. So there's only two. So this is a quantum result, again, not a classical result. And things like this can be used in entanglement experiments with Alice and Bob. But I just wanted to focus on this effect just now, that this is very strange, that you should have seen a continuum, but you only see two. No matter the initial orientations of the particles that come out, or initial orientations that go in, you only come out with two. This is peculiar to quantum mechanics. So let's keep going. We wouldn't be satisfied with that, would we, in this class? No, we have to make it more complicated. So we try to start easy, because I don't understand the complicated stuff, so I assume that other people might understand it only a little bit better. So now one of the beams from the previous Stern-Gerlach experiment is sent into a second Stern-Gerlach experiment. So you saved up your money and you bought another machine, and you put it after the first machine. So all of these particles, though, have spin up, but now this Stern-Gerlach machine is on its side. It can only deflect particles left or right. What happens? So let's go back to the picture and say we're going to isolate this beam now. Let's make it red, because red's cool, suddenly decided. So we're going to isolate the up beam. And we're going to put another Stern-Gerlach experiment over here. I can't draw it well, but here it is. And so these guys are going to go through that, the second Stern-Gerlach experiment. So if you can understand these scribblings, you're actually paying attention. Okay, so do all of the particles, are they all deflected left? Or all the particles now deflected right? Do half the particles deflect left and half to right? Or a continuum of left-right is now seen on the screen. So you took the ones that were all now spinning, measured to be spinning up from the first Stern-Gerlach experiment, and you passed them through a left-right Stern-Gerlach experiment. Is this going to give you half deflected one side, all deflected one side, or something different? So this one you could have guessed. Many of you in the studio audience and at home probably guessed this one. Half of them go one way, half of them go the other, sort of just like the first one. So even though they were all spin up, when you break them up, they're half spin left and half spin right. So the second, what might be surprising is that even if the orientation between the first and second Stern-Gerlach devices was not exactly 90 degrees, you still get a nearly 50-50 split. But we're not done yet. Here we go. Now we're going to do a third one. Don't worry, there's no fourth. So concentrate on this third one, because this is the really key one. So when they came out of the first Stern-Gerlach experiment, they were all spin up. And they were half spin down, but we forgot about those. Those went away. Boring. So then we take these and we sent them into a second one. And these were half spin left and half spin right. All right. So now we take one of these. So let's take only the right ones that are deflected and look at those. So now we know that these two groups have passed one Stern-Gerlach device and have shown themselves always to be spin up. Well, we only took the ones that were spin up. The other ones we threw away. And then the second Stern-Gerlach device was all spin to the left. And we threw away the ones spin to the right. And now we're going to put it through a third one that has an orientation up-down again. So these guys were all measured with spin left-right. One of those beams said in the third one, which is up-down, up and down oriented Stern-Gerlach device. What happens? Do you get one beam that comes out because they were all spin up to begin with here? So are they all spin up still? Do two beams come out because now some of them are spin up and some of them are spin down? So somehow they got confused again. Do you see a continuum this time because this time you've spread them out? Or does nothing come out until someone plugs the thing in? Well, you don't have to use electromagnets, so we know that's not the answer. But the answer is, drum roll please, two beams come out. That's really strange. So you used a beam of particles that came out of the first Stern-Gerlach experiment with all spin-ups. Threw away the rest. Next, you made them all spin sideways. You took only those, and then you went to see if they're all still spin-ups again. They should all, you just had that. We just had that two experiments ago. These are the same particles. These guys were spin-up. Then we measured them on their side, spin side. Now we're going to see if they're still spin-up. They're not. Half of them are spin up and half of them are spin down. So it didn't stay. It turns out that this is a very non-classical result, and it's fundamental to quantum mechanics. So it turns out that the Stern-Gerlach experiments demonstrates the act of measuring something can affect its state. So they all started, we took the ones that were spin up, we then measured them spin to the side. Measuring them spin to the side affected the up-down spin. They didn't remember that they were all spin up. And they came out of the third experiment half spin up and half spin down. The act of measuring the spins of particles in an orthogonal direction affects the quantum states of those particles, causing them to be measured differently the next time through. So this is a purely quantum effect. It gets to the heart of the nature of quantum mechanical spin as opposed to classical spin, and shows you that measuring things on one axis can have an effect of measuring things on another, supposedly orthogonal axis that shouldn't be affected classically. So with that, I will wrap this up and ask you to keep Schrodinger away from your silver atoms in your Stern-Gerlach experiment and away from your cat. And I'll see you next time with virtual things. We'll go into the virtual domain. See you next time.